Alright, time for another DraftPhysics.com video presentation. Alright, so just a snarky comment on the website. Just respond. It's just, it's so duplicitous. I mean, it's not just hypocrisy, it's duplicity. When you're grotesquely hypocritical in your position, and then you claim like somehow you're doing stuff that's you're not doing, and whatever. It's just so upside down. The spring paradox, MGT, not MGH. Anyway, you're not taking into account that the collisions with the scale also deliver thermal energy to the scale. I mean, all interactions are imperfect, but the fact is that you can make them more and more perfect. So the last video I did where they're dropping a ball bearing on hardened steel, I mean, clearly, because it's hardened steel, it's not putting little tiny dents or moving any of the steel itself, and it minimizes any kind of losses, and so you get, a very high rebound rate of your energy. It's conserved. It's lost very slowly. And, I've been over the different examples of that. So this is the part. It's just start writing down some sensible equations. Yeah, MV is an equation, okay? E equals MV, P, whatever you want to put in there. Work, everything is just movement, and it's just mass and velocity is the only thing moving in the universe, is my argument. I'm making it clear. I don't need too many equations because there's nothing complicating it. So you just follow the MV. Big M, little v, big V, little m. Big thing moving breaks into little pieces moving. That's what heat is. It's just motion in the universe. Masses moving. Little tiny bits. Starting with some basic force diagrams. Why can't you start with them? That's all my videos have been, is me drawing arrows in directions and pointing out how the arrows are exchanged. And where do you have that for gears and hydraulic systems and levers and all the other stuff I've talked about? Where's the alternative drawings? You've had 350 years to draw them. Where are the drawings? Explain just even the simple, look, I do the gravity one. I'll do that first. Anyway, force diagrams and conservation laws. So, you could even talk about just Newton's 3 laws and how I've explained how they're slightly imprecisely written. And, they say a certain truth, but they don't say it the right for the wrong reason kind of thing. Newton was guilty of a few wrong reasonings. Right answers, but wrong reasons. Anyway, so let's just go over some of this crap, and it's not much to say. Where's the competing alternative explanation? What is it? Where is it? Where can I go find the explanation for something as simple as just stuff falling in gravity? I mean, I've done the simplest example, which is you have a gravitational body and we could just set a course from point A to point B, okay? And you're probably agreeable that this is I can just draw a straight line here, and that whatever this force is, it's going to be a constant, consistent force no matter what is placed in here. There's a certain amount of gravity total net that something is going to be exposed to as it travels through here. And I could just kind of draw it as an inverse with force laws indicating photons coming off of a sun. And I have the same exact inverse square law. That is, it's separating in 2 dimensions. That's why there's an R squared law. It's because the little bits of energy, the rays, are spreading in 2 dimensions and getting further and further and further apart from each other in 2 dimensions. So we know it's a certain amount of gravity that hits here, this space between point A and point B. Now I could also draw a force diagram and explain it as if it was just essentially like rain. It's just little bits of force, little whatever you want to call it, hunks of tug, whether you think it's pull, whatever you think it is, it's a consistent amount that'll happen in this region. That's why there's an inverse square law, is because it's sort of implying there's a region in space everywhere, and that space gets hit with a certain amount. So whether you think of it as getting rays that are going to suntan you, or you think of it as water that's going to make you wet, the whole point is that what decides how wet you get, or how sunburned you get, traveling from point A to point B. And the thing that decides is your velocity. Your velocity completely controls the circumstance. So the faster you go through it, the less wet you get, or the less sunburn you get. And the slower, the more you get. So you're bent proportional to your velocity, completely proportional to your velocity. And it's clear that it's not just some, the force, the thing bending you, can't really have to do with anything else. I mean, it can't be a manifestation of velocity, because we know also from experiments where you launch things off of tables, for example, or you shoot bullets, and they fall at a constant rate, okay, that this is a constant rate, that the gravitational falling rate is irrespective of mass. That is, if you're big, you collect a lot of rain, you get a lot of photons. If you're small, not so much hit you. So the power of the force is completely dependent on the mass and the velocity combined. It'll be the combination of those two things that'll decide, and that the force is always proportional to that. You change the size of the bucket, you collect less, and if the small bucket moves faster, well, then you're going to collect the same. The impact force, that is the force of the mass itself, will be the same. And it just says, well, if you're a big thing, then you're going to collect more of the force and therefore hit the ground harder. But it's only because you're bigger. So we know that this rate, okay, the rate that you're changing this line, okay, that it's an independent thing. And so even though you could argue that, well, the faster you're going, the less arc it is, the less percentage, blah, 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 blah. No, it's a real force. It's a real amount. And it's all going to be decided by how fast you went. So where's your competing theory for this? Where do I go find it? Where's your link to your better understanding? So let's just do it the other way one more time, just to be clear as clear can be. So this has been drawn so many times. Okay, 4 units of distance and 1 unit of distance. And a simple force law is that this is happening in gravity. So there's this force hitting this size bucket. It's collecting the force, and that this collection is exactly the same as this collection. And after you've been in that gravity for that long, no matter how big your bucket is, you'll be going 9.8 meters per second. 9.8 meters per second in this location. So in 1 second, this is how far you're going to go. And it doesn't matter where I put you, where I put that 1 second of falling, this is what you're going to do. Until I get very far away and I change the 9.8 to 9.7 and then 9.6 and 9.5. And the simple argument is this is 1 second here. And you clearly only get 1 second's worth. You get 9.8 more. And so you have 19.6. Just 1 second. It's not 40 here. Okay? So there's no pointing to it and saying, well, this is really 3 units of force. Well, it's 1 second, and it's a 9.8 meters per second force. I mean, it's 9.8 meters per a second, 1 second. That's what you get in 1 second. If I made it 2 seconds, then it would be 19.6. And if I made it a half second, then it would be 4.9. So this distance doesn't mean you're collecting more, because just like going through the gravity faster, you're moving faster here. And you move this entire distance in the 1 second. It's the 1 second, 1 second, 1 second here, 1 second here. So how can you believe that there's 4 units of force here. Somehow you got hit by 4 units of photons or 4 units of water, when clearly you're only in the rain twice as long. You're only in the sun twice as long. How could you have 4 if you're only in the sun twice as long? How could you be 4 times sunburned? It's not possible. There's no rational explanation that I've been provided that counters this simple argument that there's no place to inject this extra force. I can't say, oh, it's 9.8 meters here, and then it's another 9.8 meters here. No, there's no 9.8 meters here. No, that didn't happen. It's 9.8 meters over this whole thing. This is 9.8. This whole thing. I only got 9.8 more wet. I only got 9.8 more sunburned. Not more than that. So how does this 1 plus 1 equal 4? That's your equation. That's your math. And you're telling me, oh, how could I not see how obvious it is that that's true? 1 plus 1 equals 4. I mean, it's so obvious. No, it isn't. All right. Other examples. All right, so when talking about force diagrams, I mean, I have explained how, your physics comes up with a force diagram for a circumstance. It's pretty simple. You're just going to roll a mass, okay, on a surface, and you're just going to have, this one's going to go 1 unit of velocity, and this one's going to go twice the velocity. And then you're going to try to understand what happens. Now, what you're saying is that the gravity is pushing down, and that somehow the surface has created a counter force and pushed up. Now, I would argue there's not a counter force. There's just the gravitational force pushing. And that's the only one there is. And the other one is absorbing that force, becoming pressurized by the force, and just saying, there, that's it, I'll dent this much. And all that's going to take place here is that this object is going to have a velocity in this direction. And essentially the friction is just going to be bumps and lumps that it's going to have to travel over. And as it travels over them, it's going to knock pieces off. It's going to push pieces down. It's going to break and scatter and disrupt the matter, create little tiny pieces of the matter will now start to move. So it's just going to give away movement. So that's the simple first law, is that everything just stays the same if it doesn't hit anything. So everything that's in a condition stays in that condition unless it interacts with something else, something smaller or something bigger. The fish keeps swimming, okay, unless it bangs into another fish that's bigger or smaller. Smaller one, it eats it. The bigger one, he gets eaten. Not that complicated, okay? So there's no counter forces involved. There's just things that are moving. They touch something else, and what happens is it blends this with this, and depending on how long they're in contact with each other, they share their condition, and they both become equally purple or blue or pink or whatever. The thing is, you're mixing. And what you're mixing is motion. And so in this example, there's no counter force produced by the ground. You're just going to simply leak your velocity this way into the ground. And the simple argument is when you're going slow, you're going to be going over the surface slowly. You're going to spend more time on each one of these little lumps. You're going to spend twice as much time smashing into it. And conveying your energy, and then you're going to stop here. All right, and this is going to roll, and it's going to do the same thing gravity did. This velocity will be half, so this velocity will be the same as this velocity. This starting velocity will be the same as this velocity here, and the same event that happened here is going to happen in this last little section. And this whole section, this will be 1 unit of time. And this whole section will be the other unit of time. Okay? Same time, 1 second, 1 second. This will only roll twice as long in the rolling process of exchanging. And what's going to happen is it's going to lose a lot less here, because it's going to spend less time in contact with the surface. And less time in contact meaning you can't lose as much to the surface. Now, this is more of a, if I was to be mathematically accurate, this line would be more of a curved line. But you can see that you're going to lose twice as much here as you're going to lose per foot here. And, well, it's like 3 times as much if you think about it. So where's the counter argument? So all you're doing is taking motion this way, you're banging into things, changing the motion into all kinds of motions, in the sense the heat goes in all kinds of directions. Obviously the little broken pieces can fly in any kind of direction. So the motion is being converted to other things. You're banging into them, sharing it, and the other stuff are taking it away essentially, and so this one just declines in its velocity over this distance and finally runs completely out and blends with the environment. The environment, the friction source, the surface, is moving through space in a certain way, and this now moves through space exactly the same way because they're stuck to each other and they've done all the exchanging. They've had enough time to exchange everything, and now they're both the same thing. The counter argument is, the counter force diagram is where? The source. Your theory has validated itself with what explanation of how this actually works? Where does your physics make the assertion that this goes half the speed at half the distance? Can't make the assertion because frankly it's just not true. And this is the huge giveaway. Half the speed at 3/4 the distance. That's telling you the truth. That's telling you this interaction is being controlled by gravity, and that's how I already explained how gravity works. Alright. Try another example. Alright, so let's just go quickly over the Newton's laws thing. So the first law is almost nothing. You don't have to pay any attention because it's just basically saying until something happens, nothing happens. Okay, nothing changes until something changes it. Alright, second law, Newton overtly tells you pretty much force is momentum. Okay, so you have this stuff called force, which you could understand whether you think it's some magical ray that comes out of things or some whatever field of ether that's vibrating. It doesn't matter what you think it is, but it behaves. Okay, it can do the same thing as a material object, an electron or proton that possesses it, so to speak, can behave exactly the same. So you can clearly find an equality between a force and a momentum, that is a velocity and a mass. And the two things essentially equal each other. So Newton's exact statement is, you want to go twice as fast, you apply twice the force. You want to go 3 times as fast, you apply 3 times the force, because the mass is a constant in that obvious example. So essentially there's an equality between them. It's not just a proportionality, it's an equality. So you can move something with a force itself, like gravity itself, or you can move something by interacting with something that's been already pushed by a force, that already contains the force. So it's really just the idea that this idea of motion is something inside of something. Something possesses it, and everything. To take the Newton's second law, and I should put a 2 here, and convert it into a Descartesian notion, the universe is just working based on this idea that there's a fixed amount of motion in the universe. There's stuff, and it has motion, and all you can do is make the motion into smaller things, or you can make the motion into bigger things. It doesn't really matter, it's just motion, and it's always on the move. So it never dies, and you just follow it. You just see where an interaction happened, and you know some force was exchanged, and then you can follow it back and back and back. The Earth is moving in an orbit. You could, in theory, with a right videotape, you could find every little impact, every little event where two pieces of matter or a force and matter interacted to account for every bit of the Earth's motion now, because every bit of it was controlled by interactions with force or interactions with mv, with masses moving. And the third law is the equal and opposite. Now, there's no equal and opposite, there's just understanding that when something, especially on the subatomic level, changes, the change is usually it gets bigger or it gets smaller. It expands or it contracts. Electrons go further from the nucleus, they go closer to the nucleus. That kind of thing is taking place. Or like in radioactive decay or some other kind of thing, you can understand that the atom is actually losing mass and becoming smaller, and the ejected bits, okay, are motion in the universe, and that stuff will hit other stuff and move it, and but there's no opposite reaction. So the illustration I would make of that is to understand something like the rocket engine or whatever, some vessel. I'm trying to think of the best way to illustrate the concept. Is first you have a pressurized tank, and the idea is the pressurized tank has energy hitting in all directions, so all sides are getting hit. It has an equal amount of pressure, and all you're really going to do is take that pressure. Now you could use a hose on the side here, and you can move that pressure over here, but this is just all surfaces, so all you've really done is put a hole here in the side. So even though you have the opening over here, from the vessel's point of view, from some little bit in here, it's the same thing as just saying the only stuff that can get out is stuff going this way. That's the only stuff that can get out, is stuff that actually keeps bouncing around and is going that way when it leaves. And because it's a closed container, if I close that, you could understand that it just doesn't matter that the pressure is equal in all directions, and all you're going to do is let something going this way out. And when you do that, you're going to have more stuff hitting this wall than it's hitting technically this wall, because you put a hole in it. And so you're just changing from a balanced condition to an imbalanced condition, where there's more still going this way and you gave away that way. And then the rocket adds, okay, so first it does this, and then it adds the thing where it mixes these chemicals and it causes an explosion here, and what it takes is two small atoms and it combines them into a big atom. So it creates another expansion. And that's the hydrogen and the oxygens combining to create the water molecules. So you have a great deal of expansion happening here. And the whole point of this nozzle, okay, is to basically oblige all of those collisions to reflect in this manner, and in that way create energy hitting this wall, okay, that's going to be cut into two motions, this way and that way. And now you're converting the expansion, you're taking the energy that's going this way and you're trying to get it to go either this way or this way. So you're just really creating expansion this way, and your rocket is going to say, yes, I'm getting hit this way and I'm letting stuff go that way. And the end result is your rocket goes this way because it got hit by these, and it didn't get hit by this. It's not getting hit by the flame, right? Flame's not hitting it, okay? So what is hitting it is the opposite side of the explosion. You've taken something small, made it big, and created arrows in both directions. And so it's no counter forces, there's no invented opposite forces. There's just, it's nature's generality that when something something very small, when it gets converted to something big, it's through this explosion idea. When you compress a spring, okay, you apply the force to both sides in a sense to compress it. That is, you're pushing here, this is resisting, and now you have a compression and the compression is pushing in both directions, and you can have a balance. You can stop the spring from doing anything, but that balance will be causing stress in the metal that's compressing the spring, and then you let it go, and it's just a matter of which side is going to have more mass in front of it. It'll decide which way the energy, more or less energy, goes. But it's always because of this explosion. So there's no equal and opposite reaction. And this goes back to the friction argument, where all you can do is give away what you have. The bowling ball can roll down the alley, and it gives away some of its energy to the alley. Now they oil the alley to make that minimal. And then the pins, okay, the pins will take the rest, okay? And just by hitting them and giving them momentum, for every pin you hit, this ball, the ball's motion is converted into the pin's motion. They make contact. The pin accepts the ball's condition, and the ball loses its condition to the pin. The ball becomes a little more like the pin that was standing still. The ball becomes more stand still, and the pin becomes more ball moving. So they just share their condition, and in the end, the ball and the 10th pin will both say, let's just stay here, because they have equalized their condition. Their condition will be the same. That's all. It's just giving it away. So it's basically a currency. The MV basically represents money, and all you're saying is this is the denomination. Let's see. The total amount of money, and all you can do is have it in forms, okay, of this will tell you how many nickels. This will tell you whether it's nickels or dimes or quarters. So the mass tells you how big the piece of money is, and the velocity tells you how many pieces of money. And all you're really just doing is a simple conversion. Big M's, little V's, okay, big denominations, small amounts, with lots of them, but small denominations. Lots of dimes, few quarters, and they equal each other. And that's all these conversions are. You're just converting mass and velocity between objects, and the more dissimilar they are, the more one's made out of pennies and the other's made out of dollar bills, the more difficult the conversion is, the more time it takes for the objects to settle on a transfer rate. And the closer they are to each other in terms of the denominations, nickels and dimes, it's only 2 to 1. The more possible it is to do the conversion and to exchange the money. But that's all. So a man who gives away his money doesn't need a counterforce to affect him. If he gives away the money, he's already poorer. His velocity, his number of quarters, goes down as the other ones goes up. It's just an exchange of something it possesses. So there's about 6,000 arrows in here. So this qualifies as what's called a force diagram. Alright, so it's a little bit silly to say I haven't done any force diagrams when every single video is a force diagram. It includes at least one. Alright, let's see if there's anything else. It's probably enough. I think I'll just leave it there with those examples. I mean, I could do gears and I could do hydraulics, and but I think I've already made the point that where's your counter argument? There's my force diagram. Where's your theory's force diagram for something as simple as a bowling ball hitting pins? For anything that takes place, where's your force diagram? Because you're not going to come up with any force diagram that explains how the 8-pound ball going twice as fast somehow has 4 times the momentum, the energy. It doesn't have 4 times the momentum, obviously. So, but you're saying it has 4 times the currency. Somehow it doesn't have the quarters, or the dollar bills, the money, you're saying it's twice as rich as the wallet says it is. And you just say it. I mean, you don't have any evidence of it. You don't have any experimental proof of it. You just say it. And then you question the integrity of my science? You are a duplicitite. Okay? That's all you are. A terrible, awful, snarky duplicitite. To claim my science is less detailed than your crapomatics. We're just going to invent this fake stuff. Per second. Whatever that means. Okay. Sorry. You're the one in the ridiculous suit.